All right, so here's an example of a population growth kind of problem. Um, the world population in 1900 was 1,650 million. The world population in 1950 was 2,560 million. Assuming the growth in population was proportional to the size of population. Okay, so before I even go into the problem, this is the big thing. Assuming that the growth in population was proportional to the size of the population. That again, that means that P is going to be, well, dP dt, the growth rate, is proportional to the size of the population. Okay, so we know we're in this setup, and we know that's going to give us, right, that we know from before, that's going to give us an equation of this sort. Okay, use the population growth of the world from 1900 on, and let t equals 0. Model world population growth. Yeah, I think I should say find a model of world population growth of the world from 1900 on. So t equals 0 is going to be 1900. All right, so we know what we're really trying to find here is k. The first thing we need to find is what is that percentage that's giving us this population growth. Well, we know that p0 is going to be, if that's 1900, p0 is going to be 1,650 million, which I'll just write as 1,650. We know that at t equals 50, right, 50 years later, 1950, p equals 2560. Right, so this is all part A. So I can say p 2560, right, that's p. So I'm just bringing this down here, equals 1,650 e to the k times 50. Now I want to solve for k. I'll do e to the k times 50 equals 2560 over 1650. So then I can do, I'm going to kind of do all the, I usually do it this way, to be honest. I'm going to like do all the calculator work at the end. I want to get k by itself, so I got to get rid of this e. So I will do ln both sides. K times 50 equals ln 2560 over 1650. And then I'm just going to get k by itself, so I'll divide by 50. So I get ln 2560 over 1650, all of that over 50. And when I do that, I get k equals around, what is it, 0.88%. I get about 0.008756. I'm just going to round that. Okay, so I've got my model now. I've got my growth model. It's going to be P equals P0 e to the 0.0088 t. Yeah. So I found k. I've solved for k. Now I have a model. Oh, and I don't have to keep it as P0, right? Because I know that P0 is 1650. So I've got P equals 1650 e to the 0.0088 t. The rest of it is pretty straightforward, right? So the rest of the things they ask you, use the model from part A to predict the population in 2015. Okay, 2015, so t is going to be, right, t equals 0 is 1900, so 2015 will be t equals 115. Straightforward. I'm not going to even do it. Actually, I'm going to just be p equals 1650 e to the 0.0088 times 115. Okay, that's just straightforward. Put it in your calculator. Second thing they ask you to do, and this is a pretty common example, use the model from part A to determine the year in which the population reaches 5 billion. So that's when P equals 5 billion is 5,000 million. Remember, we're doing this whole thing in millions, so remember to go back and put that in millions. So what were we asking? We're taking our model, P equals 1650 e to the 0.0088 t, and we want to know when, for what t p equals 5,000. And this is, do this, I'm going to do part of it. We'll leave you to do the rest. 1650 e to the 0.0088 t. So I'm solving for t. Okay, then I would do natural log both sides. So I end up with 0.0088 t equals natural log of 5,000 over 1,650. And then I want to get t by itself, so I get 1 over 0.0088 times natural log 5,000 over 1,650. And I'm not sure what that is, but you can do it in your calculator, and it's going to give you the number of years. It should give you the number of years. It better be past, well, we know it should be past, what did we have before? What do we have on this last one? Actually, we don't know yet, because we didn't actually look and see what B was. All right, you'll have a sense of it. Anyway, go ahead and you plug that in the calculator, and you get your answer. So that's a typical exponential growth kind of problem.